Today we're going to actually evaluate some integrals or find some integrals using the rules that you're going to need to memorize for the remainder of this year. We're going to start with some pretty straightforward and easy ones. Then next time we'll move on to some more difficult ones. So the first one we're going to look at is just an integral of 5 dx. And so we're just taking the integral of a constant here. So as we begin to start thinking about integrals, we know that derivatives and integrals are inverse operations of each other. So we have to think about a function that when you take its derivative gives you 5. Well, the easiest function that when you take its derivative gives you 5 is just 5x. Right? Derivative of 5x is 5. So 5x is an integral or an antiderivative of 5. And you're going to hear me use integral and antiderivative interchangeably. But it's not the only function that when you take its derivative gives you 5. Right? If you took 5x plus 1 and differentiated that, you'd get 5, or 5x plus 2, or 5x minus 1,000. 5x plus any constant. And so whenever we do what we call an indefinite integral is one where we've got no upper or lower limit. An indefinite integral is always going to get this plus c attached to the end of it, meaning that there could be any constant attached to the end of it. And when I took the derivative of that, I'd still end up with this integrand here, this value that's inside of my integral sum. If you forget that plus c, that's a problem. Right? Forgetting the plus c on an indefinite integral is going to drop you from 4 to a 3 on the integration state. Right? So you don't want that to happen. You're going to lose points for that for sure. So every time you do an indefinite integral, add that plus c to the end. So the second one we're going to look at here is 2x cubed. And so this, if this was a derivative, we'd be thinking power rule. Right? And so we're going to do the same thing as the power rule for derivatives, except that we're just going to do it in reverse. So what we did with the power rule with derivatives was we multiplied by the power. Right? And then we dropped the power by 1. Well, we're going to do that in reverse. Instead of multiplying and then dropping the power, we're going to actually increase the power by 1 and then divide by that new power. So this is going to look like 2x to the 3 plus 1. And then we're going to divide that by 3 plus 1, or divide it by 4. And don't forget, since this is an indefinite integral, we're going to add a constant to it. And so, of course, you're not going to write x to the 3 plus 1. You're just going to write x to the 4th. And it's over 2 if you simplify that fraction. And again, remember that plus c. And if you were to take 1/2 x to the 4th and plus any constant and take the derivative of it, you'd end up with 2x cubed. So our power rule in reverse, right, is going to be the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus a constant. So this is the power rule for anti-differentiation for integrals. And so you definitely want to know that. You're going to use it so often that it's just going to be second nature to use. So that's the rule we're going to be using for quite a few of these. Anything that can be written in a power of x to the n, well, almost anything. We'll see some later on where that doesn't work, but almost anything that can be written as x to the n, you can use that rule. So this can be written as x to the negative 5 dx. So if I'm going to find the antiderivative of x to the negative 5, all I need to do is go up by 1. So be careful with that. Going up by 1 from x to the negative 5 will be x to the negative 4. And then we'll divide by that new power, negative 4. And don't forget your plus c. This answer is fine. It doesn't look real great. It's going to be better most often if you write it like this. Drop that x to the negative 4 to the denominator. But either way is good. So here we're looking at the integral of the cube root of x to the fourth, which could be rewritten in the form where we'd use the power rule. This would be an integral of x to the 4/3 power. And we'll just use our power rule, which says go up by 1. So 4/3 plus 1 is going to be 7/3. And then we'll divide that by 7/3. Don't forget the plus c. And we won't leave it like that. When you divide by a fraction, that's the same as multiplying by the reciprocal of it. So we'll say this is 3/7 x to the 7/3 plus some constant. One of our integral rules was if we have two different functions being added together, we just integrate each one and add them together. So the integral of 5x cubed will go up to 5x to the 4th. And then we'll divide by 4. And then for cosine, well, in order to integrate cosine, we have to think about what function, when we take its derivative, gives us cosine. And that would be the derivative of sine of x. So the derivative of sine is cosine, means the integral of cosine is sine. So plus sine x plus some constant. And we're going to be using pretty much every single one of those derivative rules just in reverse while we're doing integrals. So if you don't have the derivative rules memorized, you're going to really struggle with your integral rules. So make sure you've got those all memorized. All right, the next one, we've got the integral of 8t cubed minus 6 root t plus 1 over t cubed dt. Note that my variable here is t, and then I have a dt. If those don't match up, which we'll talk about another time, then you've got an issue. For today, they're always going to match up. So the integral of 8t cubed will go up to 8t to the 4th, and divide that by 4. And then we've got 6 root t. Well, that's minus 6t to the 1/2, right? Before we integrate it. And so we can then just turn that into a minus 6. And then we've got t to the 1/2, which means we'll go up to t to the 3/2 and divide by 3/2. Well, dividing by 3/2 is the same as multiplying by 2/3. So we'll have 6 times 2/3, t to the 3/2. And then this one, 1 over t cubed, that's t to the -3. So we'll go up to t to the -2, and then divide by -2. So we have plus t to the -2 over -2 plus a constant. And we're going to want to simplify that down. That is going to end up being here 2t to the 4th. 6 times 2/3 is 4. So minus 4t to the 3/2. We're going to have t to the -2 will drop to the denominator. So we'll have minus 1 over 2t squared plus that constant. For negative x to the -2, we'll just go up to x to the -1. So we'll have negative and then x to the -1, and we'll divide by -1. And so from there, we'll end up with, well, the negatives will just cancel, and we can ignore the 1 in the denominator, x to the -1, or just 1 over x plus a constant. For the next one here, we're looking at 3x to the 5th over 5 when we go up by 1 and divide by 5. And then -2x to the -3, so we still have that -2. And then it becomes x to the -2, and we'll divide by -2. So we'll simplify that in a second. And then for secant squared, we just again have to think about, is there a function that when we take its derivative gives us secant squared? Well, yes. That function should just be tangent x. So plus tangent x plus a constant. So we've got 3/5 x to the 5th. And then the -2 cancel. That gives us plus x to the -2. Or plus 1 over x squared plus tangent x plus a constant. In the next one, we're looking at 2e to the x. Well, e to the x is the only function besides 0 that when you take its derivative gives you itself. Well, same with its integral. The integral of e to the x is also just e to the x. So this will be 2e to the x. And what function gives us secant x tangent x when you take its derivative? Well, that'd be secant x. So plus secant x. And then minus root x, right? Remember, this is minus x to the 1/2. So we'll go up to 3/2. And when we divide by 3/2, that'll be the same as multiplying by 2/3. So minus 2/3 x to the 3/2. And don't forget, plus a constant at the end there. We're just going to keep working through quite a few more of these. And as we go through, we're going to see a couple little tricks to keep in mind. This one, we'll note that the dx is actually just written up there in the numerator rather than off to the side. And that's okay. All right, because remember that dx is just something we're multiplying integrand by. So really, this is like having 1 over x squared plus 1 times dx inside of our integral. And if you think about your inverse trig functions, the derivative of inverse tangent gives you 1 over x squared plus 1. So this one is just inverse tangent x plus any constant. The next one here looks like it's going to be pretty complicated because we got tangent and we got secant in there, and tangent over secant wasn't something that we just got from a derivative. So similarly to when we were doing derivatives, you always want to try and simplify any trig first if you can. So tangent is just sine x over cosine x, and secant is just 1 over cosine x. And whenever you have a complex fraction that has the same denominator in both the numerator and the denominator, cancel those out. So this just becomes an integral of sine x dx. And if you think about it, what gives you sine when you take its derivative? Well, it's almost cosine, but it's not cosine, right? Because the derivative of cosine gives you negative sine. So in order to get sine, you'd have to have a negative cosine, because the derivative of negative cosine would give you a positive sine. So you're going to start thinking in reverse on some of these. And a lot of times you're going to have to throw the sign change in there to make it work out. And again, I'm going to post up a list of all of the integral formulas or the antiderivative formulas that you're going to need to know. So here we're now looking at 1 over cosine u cotangent u du. Let's just think about rewriting this. What's 1 over cosine? Well, 1 over cosine is just secant. And 1 over cotangent is just tangent. So really all we're looking at here is secant u tangent u du inside of our integral. We know that if we take the derivative of secant, it gives us secant tangent. So this must just be secant of u plus some constant. So the next one here we're looking at, we'll note that we're going to have a polynomial in the numerator if we were to expand that out. And we're dividing it by a singular term in the denominator, just by an x squared. And so later on, we're going to see some other techniques that on occasion might make one of these a little bit easier. But generally speaking, if you look at something in a similar form to this, what you're going to want to do first is expand out that numerator. So x squared minus 1 squared, that'll give you x to the 4th minus 2x squared plus 1 over x squared. And then we're just going to take each term in the numerator and term by term divide them all by that x squared. Right? And then that's just going to turn this into a nice, simple power rule integral. Right? So x to the 4th divided by x squared just comes out to be x squared. And negative 2x squared divided by x squared, the middle term there, just becomes minus 2. And then 1 divided by x squared is 1 over x squared, or x to the negative 2. And so now if we look at that, all it is simply a power rule integral. X squared will turn into x to the third over 3. The minus 2 will just become minus 2x. And the x to the negative 2 will go up, right? The x to the negative 2 will go up to x to the negative 1, and we'll divide it by negative 1. So really, we've got a negative 1 over x when we drop that x to the denominator. So minus 1 over x plus a constant. And it's moderately common to see something like that, especially in the multiple choice on the AP test, where you've got to simplify that polynomial in the numerator out and then divide it all term by term to come up with something that's really easy to integrate. We're going to do just a few more here, 3 or 4 more. And for all of these ones, we're going to have definite integrals. So again, the difference between a definite and an indefinite integral, all the previous ones were indefinite because there weren't any limits. But this one's a definite integral. This one has limits of integration. And so we're going to have to apply the fundamental theorem of calculus here. As we do this, we're going to find the function that is the integral of this. And then we're going to evaluate it at our upper limit. And then we're going to subtract the value of the integral at the lower limit after. But step 1 is just going to be find the actual function that represents the area underneath this curve. That we're going to find the function that is the antiderivative of x cubed plus 1, which is going to be x to the 4th over 4 plus x. Now, with all of our other integrals we've done, we added that plus a c to it. And so when we do a definite integral, we don't have to add the plus c. And we're going to, just for this first one. But after this, you're not ever going to put that plus c on definite integrals anymore, because you're going to see it's not going to matter what that plus c is. And so if I said x to the 4th over 4 plus x plus c was the integral here, we'd say we want to evaluate this now from -1 to 3. And this is pretty common notation. You might see sometimes just a single bracket over here. You might not see the bracket on the left. Or on occasion, you might just see it with a vertical bar here, right? With a -1 and a 3 on it. I'll do my best to normally just use brackets here and say -1 to 3. And so now we're just going to go ahead and evaluate this. So what is x to the 4th over 4 at 3? Well, it's 3 to the 4th over 4. And then plus 3 is plus 3. Or sorry, plus x gives you plus 3. And then what's a constant when x is 3? Well, a constant when x is 3 is just that constant. And then we'll subtract from that all of this evaluated at -1. So that'll be -1 to the 4th over 4 minus 1 plus c. And hopefully you can now see why that plus a constant doesn't matter for a definite integral, because I'm going to have to combine these, and add and subtract them, but I've got plus a constant and then minus that same constant. And that's going to happen every single time with these. And it means there's no real reason for us to put in that plus c at all. So we're not going to do that anymore. Just to illustrate it here, we've done it once, but it doesn't really, it's not really necessary. So 3 to the 4th is 81. So we've got 81/4 plus 3. And then we've got over here, we've got, let's see, this is -1 to the 4th is just +1. So we've got -1/4. And then we've got a -1. So, well, let's see here. 81/4 minus 1/4 is 80/4. 80/4 is 20. And then we got plus 3. And we got minus a -1. So that'd be plus another 1. So we end up with a value of 24. And that's all you got to do for a definite integral. find the antiderivative, evaluate it at the upper limit, evaluate it at the lower limit, and find the difference between the two. So let's take a look at another one. The integral from -1 to 1 of x squared plus 1 squared. So in order to do this, the first thing we're going to do is we're going to expand out that x squared plus 1 squared. So this will give us an integral from -1 to 1 of x to the 4th plus 2x squared plus 1 dx. And now all we got to do is just find that integral, find that antiderivative, and evaluate it from 1 to -1. So x to the 4th anti-differentiated becomes x to the 5th over 5. And then we've got plus 2x cubed over 3, and then plus x. And we're going to evaluate this from -1 to 1. So we'll plug that in. We end up with 1 to the 5th is just 1, right? So 1/5 plus 1 to the 3rd is just 1. So 1/5 plus 2/3 plus 1. And then we're going to subtract from that whatever we get when we evaluate this at -1. -1 to the 5th is -1. So that's going to be -1/5. And then -1 cubed is also -1. So that's going to be -2/3. And then -1. So I think we can see, well, we got 1/5 minus -1/5. That's 2/5. We got 2/3 minus -2/3. That's 4/3. We got 1 minus -1. That's 2. And so we're going to need to get a common denominator here. Looks like that common denominator is going to be 15. So we'll have 6/15 plus, and multiply that by 5 over 5, you're going to get 20/15. And then 2 would be 30/15. And that's going to come out to be, what, 56 over 15. It doesn't look like that simplifies down any further. 15 is only divisible by 35, right? And 56 is not divisible by either of those. Something to keep in mind here is something that we know about this particular function, x squared plus 1 squared, is that that's an even function. Right? That function is symmetric across the y-axis. Right? And we also know that we're looking from -1 to 1, which means that we have the exact same amount on the left of the y-axis as we do on the right-hand side of the y-axis. So one thing that we can do if we feel like it for a problem like this, rewrite this, -1 to 1. What do we have? We have x squared plus 1 squared, which came out to be x to the 4th plus 2x squared plus 1. You can actually, to make your arithmetic perhaps just a little bit easier if you want to, you can say this is equal to twice the integral from 0 to 1 of that same function. Right? Because we have the same amount on both the left and the right-hand side. So easy enough to just evaluate this at 0. Right? It's going to make our lives a little bit easier. So we'll see that if we do this, we end up with 2 times x to the 5th over 5 plus 2/3 x cubed plus x, the same integral we had before, but this time from 0 to 1. So now we've got 2 times that 1/5 plus 2/3 plus 1 minus, well, when I evaluate this at 0, all of these pieces just become 0. Right? And so we can see now it's just 2 times 1/5 plus 2/3 plus 1. And if we were to go through there, that's, again, 2/5 plus 4/3 plus 2. We end up with the exact same thing that we had with the previous one. which was 56 over 15. Same thing we had here, 2/5 plus 4/3 plus 2. Came out to be 56 over 15, works here. And you don't have to deal with all those fractions the second time. Right? You just get subtract 0. One thing to note, though, is be careful. Just because your lower limit is 0 doesn't mean everything inside of what you got when you integrated is actually going to come out to be 0. That's a common mistake that people make, is they say, oh, my lower limit is 0, this whole second part is 0. That's not always true. Yeah, if you've got a nice little polynomial here that's all a bunch of x's, sure. But if you have a cosine there, or an e to the x in there, or assorted other things, a 0 doesn't make those things 0. So just be careful. We'll see some of those on some of the homework assignments. Or maybe even on this problem. So we're looking at this one, an integral from 0 to 2 pi of the sine of x dx. So all we need to do is integrate sine. And so we think again about what function, when you take its derivative, gives you sine. Well, that is the negative cosine. So we're looking at negative cosine x from 0 to 2 pi. And we just plug those in. We get negative cosine 2 pi minus negative cosine of 0. And cosine of 2 pi, right? That's the same as 0, right? Same as the cosine of 0. That's just 1. So we've got negative 1 minus the negative cosine 0 is negative 1. We end up with negative 1 plus 1, which is just 0, which seems a little strange, right? That the area under the sine curve from 0 to 2 pi is 0. But if you think about it, what's sine doing from 0 to 2 pi? Well, it goes up, then back down, and then back up, right? So this is 0, and over here is 2 pi. Right? So this area right here that's above is the same as that area that's below. But when we do an integral, the value above is positive, the value below the x-axis is negative. Those two cancel out, and you should just end up with 0. And note that if we just said, oh, the lower limit is 0, I don't even have to bother subtracting the second thing, we'd end up with the wrong answer, right? Because the cosine of 0 is not 0. Cosine of 0 is 1. So just be careful. All right, take a look at one more here. The integral from 1 to 2 of 1 over x minus x. So with 1 over x, if we think about that, and try to use the power rule for that, it's going to be an issue, because what is 1 over x? 1 over x is x to the negative 1. And if I try to use the power rule for that, that means I'm going to go up to x to the 0 power, and then I'd have to divide by 0. And clearly we can't divide by 0, right? So this is not something we're going to be able to do. So we think back to when we were doing derivatives, there was a function that when we took its derivative, it gave us 1 over x. And that function was the natural log function. Right? Derivative of natural log x was 1 over x. So the integral of 1 over x ought to be natural log of x. And that's almost true, right? The integral of 1 over x dx is almost natural log of x. It's actually natural log of the absolute value of x plus a constant. Okay? And the reason we throw that absolute value on there is because when we think about the natural log function only exists for values of x greater than 0. But the function 1 over x, it can exist for all values of x, negative and positive, except for at 0. And so throwing that absolute value on there, that allows us to evaluate this integral, even if we had negative x values, which isn't the case in this problem, but it's something that we'll have to deal with other problems. So our antiderivative of 1 over x is natural log absolute value of x, and our derivative of minus x is minus x squared over 2. and we'll evaluate from 1 to 2. That ought to just give us natural log of, and now that absolute value is redundant, it's just natural log of 2. Minus 2 squared is 4, and 4 over 2 is 2. So we got natural log of 2 minus 2, and then minus, and then we've got natural log of 1 minus 1 squared over 2, or just minus half. And we know natural log of 1 is 0. So now we're just looking at natural log of 2 minus negative half, so plus half, or natural log of 2, and negative 2 plus a half would just be minus 3 halves. And that's the basics of integration, finding antiderivatives, both with definite and indefinite integrals. So just make sure that when you do your indefinite integrals without limits, that you have your plus c, and then that plus c is unnecessary when you're doing your definite integrals. When you do your definite integrals, just find that antiderivative, evaluate your upper and your lower, and find the difference between the two. So these ones have all been pretty basic integrals. Next time, we're going to get into a slightly more complicated technique for finding integrals. That's going to kind of open up the realm of possibility for what we're going to be able to integrate. And Calc 1, this class, really only kind of scratches the surface on some of the integrals that we can do. In Calc 2, you're going to learn even more integration techniques. That's going to be it for today. Next time, we're going to do U substitution integrals.